Right.
How will you choose that research topic? How do you choose a research topic when you like
how do you choose a research topic? Well, it's a couple of things. It helps if you have some idea of what you're doing. It's not always necessary. You need to have a... Okay, you basically need to be able to answer the question, if I solve this thing, will anybody care? If you don't have a good answer for that with what you're currently doing, you should stop doing that immediately. You should do something else.
But you don't have a judgment, right? When you are first PhD.
Exactly. So that's why you have a PhD supervisor, and it's his job to also, you know, gauge whether if you work on this, anybody will care. And a good supervisor will make sure you work on a problem that really a lot of people care about. The poor supervisor will pick something that everybody else has already solved and you add an epsilon. That's what makes a good supervisor. As you get older, in terms of experience, you'll develop your own taste. Some people are very good at that. Some people, well, need more time. And that's what often afterwards makes really creative researchers, right? Who then, you know, discover new cool areas where to work on, where they believe that if they solve something matters, and then they actually are able to pull it off. So you need to be able to ask the right questions, and you need the skills to answer them. And if you have only one or not the other, you team up with somebody who has the other part. So one of my favorite quotes from Wapnick about his co-author Chavanikis, so they basically defined statistical learning theory. I mean, they're one of the most influential pair of authors in, you know, machine learning and statistics, computational learning theory. So Wapnick at some point said about Chavanikis is like a tank. He solved problem, he proved theorem. And so from that I inferred that probably Wapnick was the one who was better at asking the questions and Chavanikis was better at proving it. And in some cases, asking the question is the really hard part. And sorry, I'm not really good at making Russian accents, but that's pretty much how he set it up. So just to wrap up from before the break about the clique decomposition and so on, let me show you based on an example of, you know, 3 nodes what's happening, because maybe the explanation wasn't quite so clear. Let's say I have 3 nodes, and you know they depend on each other, and I go and observe this guy here. So let's call it 1, 2, 3. So of course, P of x has to be writable as psi 1, 2 of x1, x2 times psi 2, 3 of x2, x3. So if I now want to condition on x2, so this guy here, I need to be able to compute the sum over x1 and x3, and that gives me P of, okay, that will first of all give me P of x2, right? And then, so x1, x3, and the good thing is that I can move this over, so we get here x1, x3. And furthermore, I can now compute P of x1, x3, condition on x2 is given by P of x divided by P x2. Right? Now the good thing is the x1s are not going to appear anymore, the x3s are not going to appear anymore, right? So I just have something that depends on x2. Right? And so then I have, you know, some constant times this part times that part. And that gives me exactly the conditional independence that I want. So I'll basically get that this is proportional to psi 1, 2, x1, x2 times psi 2, 3, x2, x3, and of course this variable is fixed. So that's what gives me the conditional independence. Okay. So now let's actually put our newfound knowledge to some good use. Let's do conditional random fields. So this ought to look awfully familiar to you. This is probably the third or fourth time that we're doing a chaining class. So, you know, these are what I observe. This is the latest thing. Now, the key difference to our hidden Markov model is that we don't have any arrows anymore. And that's actually a good thing here. Why is it a good thing? Well, quite often it's much easier to build a discriminative model rather than a generative model. You all know that, right? I mean, I don't know how good you are at drawing. I'm quite lousy at it. So I'm quite lousy at drawing something that resembles a cat versus a dog. I think I'm about at the level of my son. He's 6 years old. However, I'm pretty good at distinguishing cats and dogs if I see them in pictures. So my discriminative model is pretty good. I think it's pretty perfect. Whereas my generative model is way far away from a Van Gogh or a Picasso. So therefore, or a camera. So therefore, there's a good chance that also similar things ought to be the case with statistics, namely that the conditional model is much easier than the generative one. You can actually formalize that, and so Percy Young and a few others here from Berkeley have actually written papers about under which cases generative and well, discriminative models are better respectively. So this is something that you can look up in more detail. So the sufficient statistic that I'm going to use in this case is, well, let's look at this. I mean, there are some maximal obliques here, right? That's one. Another one here, another one there. So basically the only things that I need to look at are the xi, yi pairs. Okay, so those guys here. And they are the yi plus 1 pairs. Furthermore, I'm going to make the assumption of stationarity. So stationarity basically means that for the correlation between yi and yi plus 1s, which position I have doesn't really matter. So again, if I have an named entity tagger and I apply it to, well, newspaper documents, that assumption is violated. Because initially I will see a lot more entities. Then the correlation between, the x's and the y's, I just assume that this looks the same as what I would have for just, a logistic regression model. So I just have the x and y pairs. So this on its own would look like, a simple classifier. This here then, deals with the dependence between the y's. Now, for the normalization, so for this g of theta given x, I now need to sum over all the y's over the product of these terms, where the fi of yi plus 1s are just, these yi plus terms and the x and y terms collected. So this is exactly the same thing as what we saw before, just that we have a different mechanism for getting this. Okay. And we compute that with dynamic programming. Now, how would you go and optimize over that? Well, basically, we need to take the log of this, and then, let's just write out the log likelihood. We already had that before on our slides, but
Quick question on the
yes.
position. So the first line, you have psi of x with one argument, 5x.
Yeah, actually I should have written phi of x and y. I apologize.
So the first term
I'm just being sloppy. Ditto here. Those two actually depend on x and y. Yes.
So the very first term inside the parentheses should be phi of x, x1 comma y1.
No. Because the y1 is already here. that's basically my statistic for the first x and y pair. So if you just had this guy, this would be what you will get from logistic regression. Let me show you that in detail again. So remember, what we had is basically p of y given x is just e to the phi of x and y of theta minus g of theta given x. Change the color. So, and this g of theta given x, just make sure that everything's properly normalized. So this is basically the log over the sum over all the y's e to the phi of x and y dot theta. Okay, right. So now let's pick the y's to be plus minus 1. Okay. So in that case, well, what does this become? It basically, and we also pick phi of x and y to be y times phi of x. And you can check that this is actually a minimal representation of the x and y pairs, because you can basically take out the mean. Now, if that happens, well, what do we get here? Well, we'll get basically the log of e to the, y times phi of x of theta plus e to the minus y phi of x of theta. And since the y can only be 1 or minus 1, I don't really need to show it up explicitly here, right? So there we go. That's our log prediction function. Now, here we have basically x of y times y of x theta minus this. So now we can actually simplify things a lot by moving this first term into the log. And that's how we will get the logistic again. So now if we push this in, let's say y equals 1, then we'll, get e to the, well, this minus the same term, so e to the 0, plus, and here we have e to the minus y times, well, 2 phi of x dot theta. If y equals minus 1, we can play the same game, and we get it here. So I can rewrite this as x of 0 minus log of 1 plus e to the minus 2 y of x. Okay, now taking the log likelihood of this, right? Because that's what we care about. So log p of y x times is this goes away, this goes away, and negative log likelihood. That's all that remains. And this is the logistic. The only difference is that we had a factor of 2, and that's just from the way how we scaled our sufficient statistics here. Okay. So that should have been all very familiar. Any questions about that part?
We are choosing it to be of that.
Huh?
We are choosing like phi of x y is equal to y into.
So what we now have is we also have the correlation within the sequence, right? So for the correlation, we are now going to use exactly this phi y of yi plus 1. In practice, what we'll do here is we will just have a lookup table. Because basically this expression here can take on exactly 4 different values, right? Because it can either be that those two guys, I mean, if we have a binary sequence, of course, you know, both can be 1, both can be minus 1, or, you know, they can be 1, minus 1, or minus 1, 1, right? Therefore, this will just be a lookup table. So that's very easy to deal with. Now, how would we actually optimize this? Let's just erase all of that. So we have a product over I going from 1 to m. So that's the sample size. So we have yi, oops, xi, a. So we have the product here. Since it's an exponent, I can actually take it into the exponent. So we have x of sum over I going from 1 m x I yi minus, here we have a sum over I going from 1 to m x I. Okay, so that's our likelihood for these labels. One nice thing that you're starting to see here is that this problem is convex. So unlike in an HMM, where we had a non-convex problem, we had to run EM, here everything is nice and convex. Now, in order to get a proper posterior, we need to multiply times p of theta. And that p of theta is going to be something like an x minus 1/2 norm of theta squared, for instance. 1 to sigma squared, push on to that. And here we have p of theta. That's our posterior. Now I can perform a maximum posteriority approximation. So just maximize this. And that's now a convex problem. So I take derivatives with respect to take the log, take derivatives with respect to this, with respect to that and that. And the good thing is, to explain, everything is easy here except for this term here. Because this is, so d theta of g of theta given x is the expectation of y given x of, now here we have phi of x. Right? That's what we had in exponential families. And now if I only have singletons and pairs, I have over there, then again I only need to compute, you know, singleton and joint distributions of those yi's in order to compute this gradient. And that's it. Okay, so this is how you learn conditional random fields. Any questions at this point? Can everybody see this? So whenever computing this log partition function is actually difficult, you may very well end up having to sample from that if you can't really compute the derivative. So, I mean, if you have like one big monstrous graphical model, like a Gaussian Markov random, like a Markov random field for image annotation, you may not be able to compute this through dynamic programming exactly anymore. But you may be able to compute things by sampling or maybe leaf propagation or something like that. So here's what you do. You basically go and compute the distribution over the marginals. you take the conditional expectation, update either through stochastic gradient descent as what we did before, or you do a batch solver, and that's it. So, some examples. Let's take a chain. So, here's what we have, and this is what the conditional model is, right? So, basically, X conditional Y. This is what you observe. This is what's going on here. So the key difference is that this is not going to give you a nice, unsupervised technique. At least so far, nobody really knows how to do that very well. It would be nice if once could. However, if you have a problem where you have a sequence and you have hidden labels, you have some labels and you want to generalize to unseen data, then this is a good technique. Okay. Then you just condition on it and everything's good again. And yeah, we have the left-hand side and right-hand side messages, which, I mean, just look at them, you know, on the slides. What do you use it for? For instance, for name density tagging. In this case, you might have a much richer structure of how those tags depend on each other. And then, of course, this is not a simple, you know, just a JSON tag dynamic program anymore, and it actually works fairly nicely. Here's another case. So Anna McCallum did a lot of nice work on this context, Fernando Pereira as well. Here's something like trees and ontologies. So suppose I want to, for better or worse, you know, take something like the Yahoo directory or Demos and build a nice structured representation of them. And I want to learn that, right? So I have, you know, an ontology of, you know, maybe here's cars, maybe here is BMW, and here are the various models, 3X, X, whatever, and here the 5 series, 7 series, and then, you know, here you have the various cars. That's what the rock goes. Okay, fine. Now, what I want to do is, I want to have a classifier which, given a new page, will put it somewhere in this ontology. Maybe it's here. Then, well, we need to actually figure out how to build a nice graphical model which describes the distribution over all the labels, such that, you know, this document goes in the right place. So one way how to do this is to say, well, look, it's going to be one of the labels here at the leaves, or maybe not only at the leaves, but that would make things a little bit more complicated. Remember, we did this when we, in the assignment, when you had to look at classification with, you know, variable number of labels, right? So we could do the same game here by having, you know, various steps. You could just, but let's, for the sake of the argument, assume you always end up here. Then you basically could argue that the label here is actually a label of the entire path. And, well, of course, you know, things depend pairwise on each other. And here you have a potential between adjacent labels and condition also the document. So in other words, you learn separately first to tell cars pages from everything else, then maybe the BMWs from all the other cars, then the various, you know, BMW submodels from each other, and so on and so on. And that's what you store. Now, of course, storing that could be hideous. So if you look at Demos, there are about as many categories as it has editors, which tells you something about the data quality there. But you know, if you have tens of thousands of categories, it's not going to be very easy to store all the parameters. Let's say 10,000 categories times a million different words. Well, that would be about 10 billion parameters. Now, 10 billion parameters costs you something in order of 40 to 80 gigabytes of memory, which you don't have. You can use hashing for that. So remember when we talked about hashing, this is one of the places where you can use it to store actually rich ontology. And that gives you a decent model, and you can still actually solve it accurately in linear time. Now let's look at something like spin glasses. So this is where stuff gets fairly nasty. So I might have, okay, so, but you get that actually a lot. Suppose if you take a picture with your camera, like this camera over there, then, well, there is the light intensity that actually arrives on the sensor, and then is the information of whatever is being recorded on the sensor itself. And the two things are correlated but not quite independent of each other. For instance, what happens is that you have, quantum noise, because you might actually, have a very high sensitivity sensor, which, where the individual number of photons matters. It may simply be that the room is very dark, so you don't actually observe much of it, so it's a very high noise result. It may very well be that, the noise in adjacent locations is correlated. What I definitely know is that the color is correlated. So for instance, if this is white, there's a good chance that this is also white, right? So therefore, this would be a reasonable model to assume that, whatever is latent, is correlated. And this is whatever I'm observing, right? That's basically what ends up on the sensor. This is what actually I want to infer. And then a good algorithm would go and infer the blue bits from the red bits. Unfortunately, this is really nasty, and this is why by now modern digital cameras have really, really high-end signal processing processors in it. And that's why there's a big difference sometimes between the JPEGs that you get out of your camera and the image quality that you get if you put the raw image into your computer and process it with something like Lightroom or iPhoto or whatever else, where you have a lot more processing power on your computer to do the denoising. So there's a lot of work that at the moment is still going on. You might even have longer range interactions, which makes things even more messy. And so here's an example of how things progress. So there's an image of some cast in the Loire, and for instance, these two guys in 2008, they came up with an algorithm which by now works reasonably well. This is the original, and I think this is probably their solution, and that's what you would usually, this is what you start out with. And that's basically the competition. You can see that, well, they recover more than others. And people still keep on pushing this a lot because there's simply high commercial value in it. In other words, whatever you can do in software, you don't really have to do quite so much engineering on processing with the sensor itself. So over the past 5 to 10 years, probably you've gained 1 stop in camera sensitivity, maybe 2 stops, just because your processing software got better. Nothing in the sensor, just in the processing software. That's why you should always shoot raw. That's essentially the reason why. Now, in some cases, so this is a fairly interesting special case. A conditional random field, or a Markov model in this case, isn't very good. Right? So this would be classification. Each term, labeled separately, is a conditional random field where you, just look at adjacent terms. Now there are cases where you have data at very high resolution. Let's say I record user activities every maybe 50 milliseconds, maybe every 100 milliseconds. Stuff like that you get, for instance, if you instrument professional swimmers. So this was done with people from the Australian Institute of Sports, where you basically instrumented swimmers that were training for the Olympics, and we wanted to find out, which strokes they do at which time, such that otherwise somebody actually has to sit by the side of the pool and figure out, how long each of their, strokes takes, and how their cadence is improving and whatever. And it's an utterly terribly boring thing to do, to sit by the pool and always make sure you get it done to the fraction of a second. If you have 10 swimmers in the pool, you need 10 people standing there with their stopwatches and doing all the data entry. It's excruciatingly boring. So you basically can't do it. Now the idea was, well, let's instrument them with accelerometers. Can we actually detect what's going on automatically? It turns out you can, so what you need to do is, you need to go a little bit away from a simple conditional random field where you have possibly one transition at every position. So you could make these things longer range if you took a conditional random field. Let's take something like that, right? Those guys. And you put an edge here, right? This is our standard C array. Now you could say, well, actually maybe things should depend a little bit longer range. And if you do that, and maybe diagrams and so on, it actually becomes computationally very costly. Because the cost here grows exponential in the history. Now if I have a swimmer where a single cadence might take a second, then 20 segments are basically it's a non-starter, right? Because you would really have to do very, very expensive dynamic programming. It's basically 2 to the 20 or whatever number of different states you have. So you can't. What you can do though is you can say, well, actually there are two aspects to this transition. One aspect is, when did I last change my state? And how much time has passed since? So it doesn't actually matter, basically I know that in between there it has to have been the same state, but then I just get a transition. So now rather than, having long-range interactions modeled by the number of different states and longer-range interactions, I narrow down my model considerably to saying, well, all that matters is only how long ago I last switched my state and what the previous state was. So that narrows down the model considerably. Because now rather than having a exponential variety of different things that could have happened, now it actually becomes polynomial. It's basically time of the last change and what happened before that change. It turns out you can work out a dynamic program for that. It's not it's reasonably straightforward once you know that there exists an efficient solution. You can easily work it out. It might take you an hour or so, but you can easily get it. And you can use that for basically activity segmentation. So there's a few more things. So you can do proper annotation for web pages, and people have since moved that considerably further. So where you want to have overall dependency between objects on a page. So overall, I think this has turned out to be a fairly useful tool, and yeah, people are still adding lots of new stuff to it. Okay, I think that's pretty much all we had for today, and so we've now actually gone through the slides a little bit more slowly than we did before. Any questions? There's still about 10 minutes, so I could either start something new, or if you have questions, I can answer your questions. Okay?
In terms of the LLM, when you say variational methods, what is dual decomposition?
So dual decomposition, okay, that's actually a really cool thing that you can do. And so suppose I have a maximum likelihood annotation problem, and it turns out that it's really, really hard to solve that because I have various types of constraints that interact, and then what you can do is and in some cases it so happens that if I only had a subset of the constraints, I could actually solve it very easily. Just if I have all the constraints, it becomes really hard, right? So that those cases happen quite often. So for instance, it may be that I have a sequence annotation problem like this, and I'm also told, well, I can only have two guys which are maybe of one class and everything else has to be of another class. So if I just had a sequence annotation problem, things would be easy. If I just had the problem of, well, forget about all the edges and just find the two best guys in the set, that would be also easy. Okay. So now what you can do is you can basically decompose this joint problem into two subproblems, and you then use Lagrange multipliers to couple those two sets of subproblems. You basically have those two subproblems, and then the additional constraint you have is that the first solution has to match the second one. Now, the unfortunate thing is that you cannot, in general, for those discrete optimization problems, prove that you will get the optimal solution. However, what you can do is show that if you find a solution that is consistent between the two, you will have obtained the optimal solution. That you can show in some cases. So Mike Collins and co-workers have actually done an amazing amount of work in this area. So that might be a good place to start looking if you're interested in that kind of work. So, yeah, that's basically what you get in dual decomposition. It lets you solve a lot of otherwise fairly nasty dynamic programming problems a lot more easily, or in some cases even solve them at all. Yeah. Yep.
Could you give us, without the equations, high-level description of why or what changes made concave convex problem in the directed H-man case to be convex in the undirected H-man case?
Okay. So the key difference is that if you have latent variables that you need to integrate out, the problem almost instantly becomes non-convex. Okay, let me show you that in general. We have one whiteboard left. So let's look at our log partition function again, right? Or actually, let's do the following thing. So we have a simple model, P of x, parameterized by theta, is e to the y of x theta, right? Minus, take here, minus g of theta. So this is what we would usually have for density estimation and exponential family model. So I'll show you to you the simple case because it's actually the most instructive one. Now let's say we have x decomposed into x observed and x unknown. Then, well, I can easily work out P of x observed, parameterized by theta. Well, that's the sum, right, over all the unknowns of P of x. Now, what happens is that, well, this term here is a constant, so I can just pull it out. So this equals sum over x unobserved e to the phi of x observed, x unobserved, dot theta, times e to the minus g of theta. Right? So far, nothing particular fancy has happened. I've just written it like so. Now, we know, if we look at that this is just the conditional log partition function, right? So I can write this as e to the, well, g of theta given x observed. Then I'm summing over all the unobserved terms. So I get this minus that. So So what has happened now is that our likelihood for observed data is given by the exponential of the difference between two log partition functions. So where we had phi of x dot theta before, we now have a log partition function. And here we have another one. So there's a difference between two convex functions. Now if I want to maximize it, I can use DC programming as aka the concave convex procedure. And I can take a tangent of this minus that. Now, if that happens, I have to compute the derivative of this, right? So let's do that. So the derivative of this quantity here, so d theta of g of theta given x observed, is basically the expectation of x unobserved given x observed of phi of x observed x unobserved. Now this is exactly what EM does. EM tries to fantasize the unobserved data given the observed data, and then you solve a convex optimization step. So you can actually make that connection explicit. So if you do this, you get exactly the EM algorithm for unobserved data out of it. Okay. Just to wrap this up, what we have is, basically as the derivative d theta of log p of x observed given theta just happens to be the expectation of x unobserved given x observed of phi of x observed x unobserved minus, now d theta of g of theta is just the expectation of x of phi of x. So in other words, the gradient compares my idea of how the data should look like if I were to fantasize observed and unobserved observations with what I get by just fantasizing the unobserved parts given the observed ones and plugging in the actual values of the observed ones. So that's what you get by taking gradients. And what you could do is, you could basically use this in a Taylor approximation here and solve against that. And that would be then one step in an EM procedure actually. Now, this nice one-to-one match doesn't always happen, but for exponential families, it's particularly straightforward. So that's where non-convexity comes in right away once you have unobserved variables. Any other questions? So there's actually a paper that we wrote on that very thing. So. It's I think AI stats paper, and it's at least 7 or 8 years ago, so it's probably 2004, something like that. I don't recall the exact details anymore, but it's on my homepage. I mean, this is a small side calculation in our paper, so we use it for latent variables for estimation, but this is really all that you want to know from it. There's a lot more about optimization and constraints and how to relax them and the other. Don't really need that. By the way, this was then reinvented a couple of years ago. And the reinvention got a lot more popular than ours. Stuff happens. Yeah. Any other questions? Okay. Homework should be available in 2 or 3 days.